Okay, there's that. Yeah, seems like the annotation mode is giving me trouble here. Okay, maybe now it's okay. All right, so we said that the region that's entirely enclosed by this parabola, and then the lines x equal 2 and y equals 6 would be this region right here. And so I can sketch that somewhere here. I have that. What color do we want? Purple is nice. Okay, so there it is. And so we're going to imagine now, we're going to sketch the empty shell formed when the outline of this region is revolved about the line y equals 1. So lots of times, most of the time, we've been revolving around an axis. And that makes things simpler when we get to the rate function. So we're going to take it up a level here and revolve about y equals 1. Y equals 1 is that blue horizontal line, y equals 1. And so let's get a sketch of this. So we're going to sketch it. So when we rotate about y equals 1 at halfway around, so this is at 3, this point will be where halfway around? So maybe at -1, right? Because 3 is 2 units away from 1, so we're going to go 2 units down to there. And then this one, 4, is going to be at, so 4 is, well, that's 6. Is that 6? That's 6. So 5 units, so maybe -4. So I'm just rotating one point at a time. I'm taking these endpoints. This will be here at 4, -6. So do I have those? Have that right? And so then it's going to look something like this at the halfway point. Rotating around y equals 1. So then what will we get? So imagine this outline of our region rotating around y equals 1 to form this empty shell. What will that look like when it's all said and done? What kind of thing can you imagine what that will be? So what we can do is we can make some flattened, perspective circles here at the edges. So like out here at this edge, we'd have a circle like this. And then we'd be heading back like this. And then a circle like this. Okay, and then there's going to be, do you see that when we do this, this is going to create a hole on this left side of it. Something like this. Okay, and then from that hole, it's gonna do something like this. Okay, and so then the thing that the empty shell that we're accumulating, is it this kind of this inside of this funnel here, or is it the kind of the outside region here?
Could you repeat that question? You cut off for a bit.
Okay, sorry. So the where we're going to accumulate volume, right? So I kind of made this sketch. Are we going to accumulate volume kind of inside the funnel or kind of around the outside?
Around the outside.
Around the outside, right? Because that's our region. Our region is this purple, and so we're going to be the stuff is going to be in that outside. So it's kind of like a funnel, right? Like kind of a thick plastic funnel. Okay, so and we're accumulating the volume of the plastic part, so that when we're all said and done, it can funnel, stuff through this way. Okay, how are we doing on the empty shell? Are we good on the empty shell? Any questions so far? All right, so we're working through the steps here. We're going to imagine x increasing through delta x intervals to form cylinders that fill this shell. So if we do that, what's our independent variable? What's going to be our independent variable? X, right? So if we're going to create delta x intervals for this, like this, and then x is going to increase through delta x intervals, creating these shells that are going to grow and fill up the shell, and we're going to accumulate the volume of these cylinders. And so here we go. Moving along here. So we're going to mark off the delta x intervals. I did that. And so maybe I should I'll make a few less, a little bit bigger here. We'll do that again. Let's do this. So maybe I'll just make 4 of them. That's better. Okay, so we got delta x intervals like that. And now we're going to do our typical strip in a delta x interval, and that's going to be in the region. So I'll just come here to this the second interval here. So starting at the second interval, I'm going to drop like this. And let's change the color of that so my black shows up a little better. Okay, that's better. So we're drawing typical strip here. And then that strip, we want to imagine that we're growing, delta or x is growing in that interval. So we're just going to pick an arbitrary x inside that interval, right? An arbitrary x. So just say right here. And then we're going to keep the y value the same as it was at the beginning of the interval there. All right, and then we're going to revolve that strip in the current interval, right? How wide is that strip? What do we call that width right there?
dx.
That's dx, right? It's varying through the current interval of delta x. So that strip has a width of dx, and we imagine as x increases, that strip is getting wider, right? It's going to start at 0 width, and it's going to end up at delta x width, right, in the current interval. And so we're going to take that, we're going to pause x right here. We're going to revolve that strip around y equals 1 the same way we did the region. And so that's going to give us something like this. Okay, and so we imagine, what are we going to get? So we're going to get, imagine revolving that strip around the y equals 1 line, and we're going to get a typical something like this. So that's going to be, and we said the width of that thing is dx, right? Okay, and so is this, as the x increases through this delta x interval, does the cylinder grow in radius or height? Does it grow in radius or height?
Height.
Height, right? This is up on its side. What's growing is this dx is growing, right? Dx is growing. That's the height of this thing. And so if the cylinder grows in height, then the rate of change is. So the rate of change, we're going to call this rate of change 1.
Area of the base.
Area of the base. Area of the base, right? So this area, right? So it makes sense because what are we adding on? What are we adding on to that little bit of volume? We're adding on like a really thin piece like this, right? It's the leading face, right? It's the leading face of this thing. So what I just shaded in black is if x increased a little bit, that's how much volume would get added on, right? So that's the rate of change of volume. That's how fast the volume is growing. It's growing by the amount that we would add on as x increases. That's why it's the area of the base. Okay, and so what's the formula for that? We got a hole in it, right? So it's going to be our pi r squared, but there's going to be a hole. So we're going to have the pi r outer squared times the pi r inner squared. Okay, and so now for these radii, this is when we ask, for the outer and inner radius, this is when we ask, is it a x-coordinate, a y-coordinate, a big change in x, or a large variation in x? Yeah, a large variation in x or a large variation in y. So let's do one at a time here. What should we do first? Let's do the outer radius. So the outer radius of this thing is from here to here. That's the outer radius. And so in the picture, where's that? The center is it at y equals 1 or y equals 0?
1.
1, right? Our rotation was about y equals 1. So the outer radius is going to be like this right here. What is that outer radius?
2.
Oh, so first of all, is it a x coordinate, y coordinate, large variation in x, or large variation in y?
Variation in y.
Yeah, so now we're getting to an example of variation in y. This radius starts at 1, doesn't start at the x-axis, it starts at 1. So it goes from 1 up to 6. So that's a large, what we call a large variation in y. So to do that, we do y final minus y initial. Now in this case, that's kind of overkill. You know 1 to 6 makes 5. You could just write 5 down. That's fine. But notice 5 is not a y coordinate, right? It's not, the y coordinate of 5 is here. That doesn't relate to this radius. That's why we call it a large variation in y. Okay. All right. Minus inner radius. So the inner radius is also from this rotation to where the hole ends, right? Right there is our inner radius. And so, again, large variation in y. So we're going to do y final minus y initial. So what is y final? What is y final for this? Should be the
1/4 x squared plus 2.
Okay, so it's just whatever, it's the y coordinate on this curve, right? It's the y coordinate on this curve. So I'm going to write it as, just to start, I'm going to write it as y final. But so that's so just y, I'm sorry. It's the y coordinate on the curve. So y final is the y coordinate on the curve, and y initial is 1. But so that would be our kind of starting point here for the rate of change function. Pi times y final minus y initial for the outer radius minus pi times squared, sorry. Pi times y final minus y initial for the inner radius. Now we're going to change that into x. Well, that's just 5 squared. So what is y in terms of x?
1/4
x squared plus 2.
So it's like that. And yes, 2 minus 1 is 1. So if you simplify this, you get plus 1. So we got it. We got our rate of change function as a function of x. Any questions on that? And so then, how can we write the volume accumulation function? So the volume, call this v1, the function of x. Okay, so we want to start accumulating from where?
x equals 2.
Yeah, the first cylinder that looks like this, right? The first cylinder is here at x equals 2, up until x. And then how much volume have we accumulated up until x equals 2?
Some value of x. Or what?
So before we got to 2, how much volume got accumulated?
Nothing.
Nothing, right? That's where we actually truly start. There's no volume accumulating over here. So if we want to write a total accumulation version, it would just be 0 plus, or v of 2, which is 0. But be careful of using, when you're defining, v1 of 2, when you're defining it in GC, you can only use a function value in a definition if GC knows what that function value is. So in this case, if you put v1 of 2, it would not know what you're talking about. Okay, so if you want to write it as a total accumulation, you would use 0 plus. Okay, and so then what can we write here? I want to make this as easy as I can on myself. What should I write right here?
R1 of x, or R1 of t.
Good, use function notation, right? This is kind of, now this rate function is getting a little longer, more complicated. We already did the work to figure it out and write it down. Use function notation, right? R1 of t dt. especially in GC. That's really convenient too. All right, questions on using x varying through delta x intervals.
Yes. So the radius for the inner and for the outer radius,
Mhm.
you would say that that was a large variation in y.
That's right. Do you understand why?
Is it because you have these two lines, like it's in a defined area?
It's because, so the other possibility would be a y coordinate, right? But a y coordinate is always a distance from the x-axis. So notice, what did we get for the outer radius? We got 5, right? Which was this distance from here to here. That has nothing to do with a y coordinate of 5. See, here's a y coordinate of 5. That has nothing to do with the fact that this outer radius was 5. So it was 5 because it was a big variation in y starting from 1 going up to 6.
Right, because for the 5, it was just from the x-axis, but for the r inner and the r outer, it's from the 2 to 6.
1, yeah.
1, sorry.
Yes, yeah. Because we're rotating around y equals 1, these vertical dimensions are not y coordinates anymore.
Right.
So this is what we call it. We call it a large variation in y, right? So from here to here.
Thank you. Yeah.
Yeah, sure. Other questions?
Yeah, I missed when we wrote the volume equation
Uh-huh.
where we got the 0 from.
Talking about all the accumulation before x equals 2. How much volume have we accumulated starting back here up to 2?
From negative infinity
Sure.
to 2?
Sure. Yeah.
Oh, okay.
Nothing, right? So this thing doesn't start until we get to the bottom of our funnel, right?
Okay.
So I was just talking about if we wanted to put this in the form of total accumulation, we would need this initial value, right? This all accumulation before 2, which is just 0. And it usually is for these volume problems.
Professor,
Yeah.
If you could scroll up just a little bit, because in I believe the second part of the equation, it says y minus 1, which is in the brackets. So is 1 over 4x to the power of 2, okay, that's what y equals to. Is that why we're plugging it in as we're solving?
So this inner radius is from 1 up to this curve.
Yeah.
So the y value, so that's just said, so I just said y minus 1. But our function is in terms of x. Our function is in terms of x, so we got to change that y in terms of x.
Right. Okay. Thank you so much.
Sure, sure. Other questions? Okay, so we're gonna do it for y now. So why don't you take, let's see. So we're going through the same steps again. We've already, same shell, right? Same empty shell revolved around y equals 1. And so now these, start doing these questions here. Let's see my screen. And then, but all for y. So imagine y increasing through delta y intervals. What's the independent variable? Mark off delta y intervals. Draw a typical strip in a delta y interval. As y increases through delta y intervals, does this cylinder grow in radius or height? Find what is the volume rate of change function? Yep. So then you're gonna change it into in terms of y, in terms of the independent variable, and then we're gonna rewrite the rate of change function. So see, work on this for a couple minutes. I'll kind of wait a minute or two, and I'll trail you. See if you can get ahead of me and make good progress, and then you can just check. You can just check how you're doing as I'm writing, but I'm going to wait a minute to start. So see if you can stay ahead of me. Doing the same set of steps for the same empty shell, but now with delta y intervals. Is the task clear?
Sir.
Okay, give it a shot. Pretend this is a test question, or pretend you're studying for the test. The test is tomorrow, and you got to get this right.
Professor,
Yeah,
we're still revolving around y equals 1.
it's the same empty shell. You're going to take the same exact empty shell where we took that region and revolved around y equals 1. The only difference now is we're gonna have y increase through delta y intervals for the same empty shell.
Okay, thank you.
Sure.
Hey Mark, this is Steve. I've gotten a few questions about how you determine whether you use a piecewise rate of change function.
Okay. We'll actually, hopefully, we'll get to that at the end.
All right, good.
But just to address that now, the reason, so why did we not need a piecewise rate function for this one? The reason we did not need a piecewise rate function is because starting from 2 all the way to 4, these cylinders were exactly the same in their structure. The inside radius was always determined by this curve from 2 to 4, and the outside radius was always determined by this curve from 2 to 4. So if along the way, what defines, say, the inner radius, if that would have changed from this curve to something else, we would have needed a new piece for a different rate function. Or if this outer radius, if something would have changed along the way here from 2 to 4. But because it was the same curve from 2 to 4, and that was the same line from 2 to 4, we did not need to split it up. So hopefully that.
I'm going to answer a question verbally that I've gotten on the chat a little bit. So
Sure.
the piecewise function, that is not dictated by whether or not your cylinder is hollow. So
Right.
this cylinder, these cylinders here that we're generating, they're all going to be hollow, but keep in mind you do not need a piecewise function because the same pair of functions that you're using for your inner and outer radii, those are effective for the entire interval. You do not need to change your behavior. Like, think about the one we did in recitation with the trapezoid.
Okay, so hopefully to this point, what's in these cylinders, in the current interval, how do these cylinders grow? By radius or by height?
Radius.
Radius.
Radius. These are growing by radius, and therefore our rate of change function will be? So this will be rate 2 as a function of y now.
2 pi RH.
Right, so you think about if y increased a little bit, where would the volume be added on? Where's the volume being added on? It's being added on here. And so you imagine a really super thin sleeve around there. That represents how much more volume you would get when y increases a little bit. That's why it's the rate of change of volume, because that's where where the volume is being added on. So that the magnitude of that is like the next little bit of volume that you'll get. That's the rate of change of volume. Okay, so that's 2 pi RH. And so for each of R and H, we've got to ask. So let's do the radius first. Radius. X coordinate, Y coordinate, big variation in X, big variation in Y.
Variation in Y.
Big variation in Y, right? It's going to be from the center of rotation at Y equals 1 up to what the current Y coordinate. So it's going to be, so Y final is just, this is just the radius is just Y, whatever the Y value is at that moment, minus 1. Okay, the height of these things. Big variation in X, big variation in Y, X coordinate or Y coordinate. So the height is on its side here, it's this.
Big variation in X.
This is a large variation in X because we're not tracking, or our reference point is not the y-axis, but it's from here. So it's from here to here. So what's that going to be? It's going to be the x coordinate on this curve minus, so we're calculating this distance, x final minus x initial. What's x initial?
X equals 2.
2. So this big variation in x, which is the height, is going to be the current x coordinate minus 2. So now we need to write this in terms of y. Well, y minus 1, we're good. It's already y, right? So just leave y minus 1. So what is x? The x coordinate of what? The x coordinate of this parabola, right? Which was y equals, was it 1/4 x squared plus 2?
Yes, sir.
So we need to get, we want it to be x, but written in terms of y. So it's going to be y minus 2 times 4 square root. So y minus 2, subtract 2, we're going to multiply by 4. And then we're going to take the square root of that to get x. And that whole thing is then minus 2. Anybody get that before I did?
I got the beginning part of it.
Okay.
Not the
So, would you have gotten it? Could you get it? Question on that. So that's the key thing. Does it make sense? Ask if I lost you.
So basically, kind of just to recap now that like our parameters are like we have this y equals 1 and x equals 2, or like I'm not sure if that's right. I don't remember what the original equations are, but we have to take that into account when we're looking at like the radius and height, and that's why it's a variation in x and a variation in y, right?
Yeah, because our original region here, so everything, to get to these points on these curves, it's vertically, it's the distance from y equals 1 now,
Yeah.
not from y equals 0. If it were from y equals 0, these would all just be y coordinates.
Okay, that's what. Yeah, I just.
But we're coming from y equals 1, so it's always kind of 1 less than the y coordinate.
Yep. Okay, perfect.
Yeah.
I think I'm getting it.
Okay, cool. Nice.
But for the x value where we said the height was a big variation, x, it wouldn't matter if we had that, like if it was rotated about the x-axis, it would still be a big variation.
Yes, exactly. So that, yes, the fact that I have a big the reason for the big variation in x here is because the region starts at 2, not because of this rotation line.
Yeah. Okay. Thank you.
Yep. Exactly.
So then for the volume, would you just do it from where, like, since it's at 1, would you plug 1 into the y equals equation to find out where the integral starts?
Okay, so yes, so now in terms of accumulating volume, it starts here. So, right, is that what you're saying?
Yeah.
So yeah, so in terms of like the net accumulation of volume, we need to figure out what that y coordinate is right there. And that's the intersection of x equals 2 and our parabola. So I think that's 3. If you put x equals 2 in, that's 4.
Yeah.
You get 1, that's 3. So this y coordinate is 3. So now when we write v2 of y, again it's going to be 0, nothing, plus starting from 3 at this rate. Okay, questions. So we got a couple minutes left. I want to show you a variation on this where we actually get a split rate function. So, questions on the rate of change of y?
I just have one question. How did you know that it was 3 to y? Is it just from the graph? Like
Yeah, so it starts, in terms of y, we start accumulating volume right here. And so that's the intersection of x equals 2 and the parabola, right? This point is on the line x equals 2. It's also on the parabola. So when you combine those, x equals 2, you get y equals 3.
Oh, okay. But we would have to calculate that on the test, right?
Yeah, I didn't. So like, if this was the problem, I did not give you that starting point. Yeah, it just told you these 3 equations, so you'd have to come up with that y value.
Okay,
Thanks.
Sure.
I have a question.
Yeah.
I guess I'm still just a bit confused on conceptualizing when we're adding area to the base versus the lateral side.
Okay.
So over here, how is it that we're adding area to the lateral side?
Because in the current interval, as y increases, then this thick. Do you see that this thickness increases? dy is increasing in the current interval,
Okay.
and that's because y is increasing. And so that's the outer radius increasing. Do you see that? That's that outer radius. That's what's increasing here.
So then why is that not the area of the base?
Because the base is this little thin ring right here. That would be if it was growing this way. So as y increases, this thing that I've shaded, that's what's getting larger. The next little added volume is like a sleeve that wraps around this. That's like that black that I just shaded. So if that's how much, the little bit of volume that's being added, well, that's the rate of change of volume.
Okay, all right, I see it now. Thank you.
Cool.
Professor,
Yeah.
sorry to just kind of like talk on what she just said. So the thickness is increasing. As y increases, dy increases.
Mm-hmm.
The thickness increases. So why is it affecting the lateral side of the cylinder? Like, why is it affecting the outer surface area, not the
Because if this was at one point, then if the y is increasing, if the radius is increasing, then in the next moment it looks like this. And then the next moment it looks like this. So what's increasing? This is increasing.
Oh, okay, right. The x value in this.
Go back and look at the videos of those previous. Look at the previous animations I showed in previous classes. That really will help. But I think did that do it?
Okay.
I was just gonna say that Tuesday in recitation, Stephen, he gave a really good if you imagine rolling toilet paper back onto a roll.
Yeah.
Was just a really good way to
conceptualize. Yeah, it's good. Yeah, it's like the next layer of toilet paper. Yeah, you're putting toilet paper back on. Right, exactly. And that's going to be the increasing radius. Thank you. That's really good.
Professor?
Yeah.
So when we were doing x increasing on delta x intervals, we we made like a hole in the cylinders that we were making.
Okay.
So why didn't we do something like that for y values?
You just have to imagine, that we draw a typical strip and we rotate the typical strip the same way we rotated the whole thing to get the shell. So here do you see our typical strip is like this?
Yeah.
So what do you get when you rotate that typical strip around y equals 1?
Okay, that makes sense.
And then so here's a typical strip for x. What do you get when you rotate that typical strip around y equals 1?
You get the cylinder with the hole through it.
Yeah.
Okay, that makes sense. Thank you.
Sure.